All right, so hi everyone, and welcome to my talk. So this talk was originally titled Practical AI, Building an LLM-Powered Organizational Bot in Node.js in under 2 hours. Then I realized we can actually do it in under 1 hour, which sounds a lot better, right? So I changed the title. Then I came across some code that shows how to do it in about 12 lines of code. So maybe we need to change it again, I'm not sure. This is the code, by the way. And you can copy and paste it and run it, and it works. But what is really going on here? How does this work under the hood? And how can I customize it and tailor it to my own specific use case? Also, is this going to work out of the box in production just like that? And, oh. This is Python. Okay, you're at the right conference. This is a Node-related talk. You know, there's been a lot of hype about LLMs and RAGs and AI lately, and maybe you've built some software with LLMs yourself. Today, we're going to look at how a knowledge bot really works under the hood, and we're going to do it in JavaScript, in Node.js. I only have 30 minutes, so I had to simplify some things. Just a disclaimer. Speaking of disclaimers, my name is Roy Moore. I'm a software developer and architect. I currently do AI engineering at BlinkOps. Blink is a platform for generating security and DevOps automation workflows with no code. Prior to that, I was a consultant and a software architect and a tech lead and a software engineer at a bunch of other places. So, Gen AI is changing the world and is everywhere, including LLMs. But the real power of using LLMs comes from integrating them with your own knowledge base and getting data on our own knowledge base, basically. So the use case I have in mind is this. You're a developer, and your organization has an internal knowledge base that could be stored anywhere, really. And let's assume that it's comprised mainly of text files. And your task, if you choose to accept it, is to build an internal question and answer bot that can correctly answer questions phrased in natural language based on that organizational data. And my question is, how? How do we approach this? Where do we start? So this is going to be the topic of this talk, and maybe a good place to start is to imagine what are the elements or the building blocks of this system. So the first building block is the LLM, the large language model. Then the second one is a vector database. Then there's something called an embedding model and an ingestion pipeline. Let's start with the LLM. So everyone who's used ChatGPT knows what an LLM is. LLMs are neural network-based model that can parse text and generate text, and there are commercial ones and open source ones and so on. But the important thing is they're all accessible using an API, right, that they expose. Now, the basic unit of input and output for an LLM is the token. A token is usually a word, but can be less than a word. It's roughly around 4 characters. This is the term that we're going to use from now on, a token. What is a prompt? Everyone knows what a prompt is, right? A prompt is the text provided to a model before it begins generating output. So when I'm playing here with ChatGPT and I ask it to explain the theory of gravity to a 6-year-old, that is the prompt, right? Well, not entirely correct, because when I chat with ChatGPT, I'm not speaking directly with an LLM or even with an API. I'm using ChatGPT, which in itself is an LLM-powered app. It's a web app that interacts with the LLM under the hood. And what it sends to the LLM, along with my query, is something called a system prompt or a meta prompt that's hidden from the user. It looks like this. This is ChatGPT's hidden system prompt. If we zoom in, we see that it has a bunch of instructions to the LLM. You are ChatGPT, a large language model trained by OpenAI based on the GPT-4 architecture. Then a bunch of tools and instructions. Browser, you have the tool browser. Use browser in the following circumstances. If the user is asking about current events or something that requires real-time information, or the user is asking about some term that you're totally unfamiliar with, and so on. Maybe more interesting are the instructions for DALL-E, GPT's image generator, which is included in GPT and ChatGPT. An interesting instruction is do not create images of politicians or other public figures. Recommend other ideas instead. Did not create images in the style of artists whose latest work was created after 1912. Diversified depiction with regard to descent, gender, and so on. Quite interesting. But why am I showing you all this? Well, two reasons. The first one is because I think it's super cool, because that's an example of a new programming model where we use natural language, English, rather than code to give instructions to a machine. Think about it. This would have been pretty hard to implement using a bunch of if clauses. But there's another reason, and the reason is that we, as creators of a bot, can and should also use a system prompt. So if our user is asking the bot a question like this, what we end up sending to the LLM might be this. This is called a prompt template, where we inject the user question with a system prompt that has instructions to the LLM, emphasis, restrictions, maybe the style and tone of the answer, and so on and so forth. And the last LLM-related concept that I want to talk about is the LLM context window. Basically, the context window is the amount of text that the LLM can consider at any one time when generating a response or processing text. This window is the maximum number of tokens that the model can look at while making predictions. It's basically, you can think about it as the model's short-term memory or the field of vision, and that's limited. It includes both the input prompt, so the user's question or query plus any system prompt, and the actual output generated. And each LLM has different maximum size of context window. So let's go back to our problem. We'd like to connect the LLM to our own internal knowledge base. How do we do that? How do we give LLM access to our org knowledge or knowledge? So maybe it's worth understanding what are the ways we can provide knowledge to an LLM. The first one is pre-training an LLM from scratch. We're not going to do that. Another option is fine-tuning an already trained model by providing it with thousands of input and output examples, and that's that we need to create that. That's actually not a very good way to provide domain knowledge, and also not cost effective. And there's a third way, which is to provide the knowledge to the LLM in its context window or its prompt and ask questions about it. And this is the route that we're going to take. And because LLMs have some reasoning abilities, they can use this new information provided in the context almost like information learned in the pre-training stage. What happens when the LLM doesn't have domain knowledge and we ask something related? They either respond with I don't know, or they hallucinate. Because they're probabilistic machines, they just select the next token. They might select output text that sounds very convincing because it's probable, but it's completely wrong, and that's a hallucination. Just as an example of I don't know, a few months ago, I gave a talk at another conference, and prior to the talk, I went on ChatGPT and asked it to list all AI-related talks in that conference. And the response was, I'm sorry, I cannot provide real-time or location-specific information, such as the list of AI-related talks at the API conference in London. My training data only includes information up to January 2022, and so on. So many words just to say, I don't know. But what happened when I went on the website for that conference and copied the schedule, the program, and then pasted it into ChatGPT? Just before that, I asked in the prompt, answer the questions based on the data provided, and then I pasted the program. Monday, Tuesday, Wednesday was a long conference. And then at the same prompt, I asked, list all AI-related talks in API Conference London. I got a pretty good response. So I got a list of all and only the AI-related talks. This wasn't an AI conference, by the way, including the talk title, the speaker's name, some nice commentary at the end, and so on. So maybe we can do the same thing. Not with ChatGPT. Why can't we just get all our organizational knowledge and pour it programmatically into the context window? And we can't really do that. That's not a good way to teach LLMs knowledge about our organization. There are two reasons. The first reason is the context window is limited, and although newer LLMs come with growing windows, Gemini Pro has a context window of 1.5 million tokens, which is huge. But even so, our entire organizational data probably doesn't fit in 1.5 million tokens. Also, this is not a very efficient way engineering-wise. We don't want to send our entire Google Drive to the LLM for each user query. Also, we pay by the token. Tokens affect latency and so on. So this is one reason. The other reason is that context window stuffing doesn't work. Context window stuffing is an act of trying to stuff as much information as possible into the context window until we max out of tokens. And research shows that this is not a good way. The LLMs perform very poorly. They tend to ignore everything in the middle, just like humans, and so on. And there are other reasons. The bottom line is that we, as much as we want to, we can't really use this method. We need to provide the relevant pieces of information relevant to the user query in the prompt. So, where do we stand? We'd like to implement a knowledge bot using an LLM on our custom knowledge base. And we'd like to provide the knowledge to the LLM in its context window or its prompt and ask questions about it. But as much as we'd like to, we can't provide our entire knowledge base to the LLM in the prompt. We need to provide the most relevant content in the context window or the prompt. So we want to build a system that automatically finds the relevant content to be used as context based on the user query, which is dynamic and is determined at real time by, well, the user. And the solution is RAG, Retrieval Augmented Generation. Maybe you've heard this term that's hyped a lot lately. Generation is the act of the LLM generating a response. Retrieval is we retrieving the relevant context and feeding it into the LLM. Hence, the generation is augmented by the retrieval. Basically, RAG is just a fancy way of saying, put it in the prompt. But there's a bit more to it. So RAG is an architecture that looks like this in high level. So when a user makes a query, we go to the database and retrieve the most relevant documents for that query. We'll see how in a second. And then we feed them to the LLM along with the user's query. Now, the LLM has a prompt with context, the user question, plus the relevant information, just like what I did with ChatGPT and the conference in London. But how do we know which documents to retrieve per user query? This is where the second building blocks enter. Vector database. Maybe it's worth saying something about vector embeddings before we talk about vector databases. So vector embeddings are numerical representation of data such as text, images, audio, video, just about anything. We're interested in text. So a whole paragraph of text can be reduced to a vector, and that's called embedding. This is an n-dimensional vector in n-dimensional space, but you can just think about it as a very large array with numbers. And embedding, reducing text to vector, is done using something called an embedding model, which is a type of LLM. It's a language model of type encoder that we give it a text chunk, and it inputs out a vector representation. The nice thing is that vector embeddings can capture the semantic meaning of text and the sense in which words and expressions are used. So words, paragraphs, expressions, and so on with similar semantic meaning will have similar vector representation. And that means we can run semantic searches, similarity searches using vectors. So for example, if I have a database of animal names and someone runs a search for a furry animal that barks, it would output dog, fox, and prairie dog if I only knew what that was. But this is something that you can't really get with classic keyword lexical search. All right, so the embedding model is the third building block here because we use it to transform text into a vector. Vector databases are what we use for semantic search. It's a kind of database that indexes and stores vector embeddings for fast retrieval and similarity search, and has all the usual features that we expect from a database like CRUD operations, metadata, and so on. So the depiction should look like this. That database is actually a vector database. Good. So now that we know all that, we're ready to implement our RAG, at least on the board. RAG has two phases. The first one is the data indexing phase, where we store all our knowledge-based content as vector embeddings in a vector database. And the second one is the retrieve and generate phase. This is what happens in real time when the user makes a query, where we retrieve the relevant context and we generate the response with the LLM using that context. So let's start with the data indexing phase. It looks like this. We start with our knowledge base. The first step is data loading. We want to fetch all the data from all the data sources and either load it into memory or store it into files so we can process them. What kind of processing? This is the second step. It's called data splitting or chunking, where we split those documents into smaller pieces, usually paragraphs. Why do we have to split them? Well, because we want to vectorize them, to embed them in order to capture the semantic meaning. Now, if we embed entire files or even pages, there's a lot of noise that's we introduce. It's not granular enough. On the other hand, if we only embed sentences, then of course it's very granular, but we lose context in the bigger picture. That's why we usually embed paragraphs. The third step is data embedding or vectorizing, where we convert the chunks into vectors using an embedding model. So one chunk gets one vector, and we can create metadata while doing so. And the last stage is that of data storing, where we save and index each data in the vector databases along with the metadata. What do we save? Well, we upsert each text chunk along with its vector representation and some metadata. It can look like this. So we see 3 items here, a vector, a truncated chunk, and some metadata. We can see that the first 2 entries are from the same file, right? Because of the metadata, the third one isn't. This is how it looks. So data loading, data splitting or chunking, data embedding or vectorizing, and data storing. So once we do that, we're good to go. We have all our organization knowledge in a vector DB ready to work against. But most knowledge bases are living creatures. So documents get added, deleted, modified, and so on. And we want any changes that happen upstream to be reflected downstream, so our bot user will get up-to-date information. This effectively makes the whole thing into an ingestion pipeline that could be either triggered by any change or scheduled periodically, once a day, once an hour, or batch. In any case, the third building block is the ingestion pipeline. All right, so we're done with data indexing. We're done with pre-processing. What happens in real time when the user makes a query? This is the retrieve and generate phase, and it looks like this. So the user asks a question. The question is a string, right? So we can use the embedding model to transform that question into a vector embedding that captures its semantic meaning. It's very important that we use the same embedding model as the one in the data indexing phase, so we can use the same metric and compare apples to apples. So we get a vector back, and we can talk to our vector database and run a similarity search and ask, give me all the text chunks that are similar semantically to the user question, hoping that they'll also be relevant. We get back the top K matching text chunks. K here is a number, it could be 5 or 6 or 8. So the top 5 text chunks that are most similar semantically to the user query. And now we can feed that to the LLM. So now we feed it, there's a user question and text chunks. Prompt with context. It might look like this in a prompt template. And the LLM reasons about it, returns the answer to our app, and we send it back to the user, and everyone's happy. So in high level, it looks like this. The user asks a question. We convert the question into a vector embedding using the embedding model. We search the vector DB for the top K chunks semantically similar to the vector. We get them back. We query the LLM using those chunks as context. The LLM responds, and we send it back to the user. This is how the retrieve and generate phase looked in the general picture of all the RAG system. This is the data indexing phase. And this is the whole thing. Indexing phase plus retrieval and generation. I'm going to leave this on the screen for a second so I can have a sip of water. Good. So now we've implemented RAG on the board, and we have a clicker exception here. Okay. Fall back to keyboard. Ooh. So let's build it. We're ready to build it in JavaScript? All right. So before we build it, we need to make some choices, some implementation choices. For an LLM, I'm going to use one of OpenAI's GPT's models. For the embedding model, the OpenAI embeddings. For a vector DB, I'm going to use Chroma, which is an open source vector database that we can run locally. I'm going to use JavaScript this time. And I'm not a big fan of LLM libraries and framework, but for this specific use case, it could come in very handy. So I'm going to use LangChain.js that will act as an orchestrator or ingestion pipeline. So, and what are we going to run on? What is the organization knowledge that we're going to use? So turns out that GitLab has its entire company handbook, its entire wiki online publicly on the web. And it has company information and people group information, and security, engineering, marketing, and so on. There's a few snippets. Quite interesting, really. The nice thing is that it's available as a repo on GitLab. So we can clone it and use it as our data. So this is the demo. The demo code can be found here. And we're going to try something very risky. and do a live demo here. Okay, let's see. So this is VS Code. I'm running Jupyter Notebook with Node.js. These are the prerequisites that I'm installing: LangChain, OpenAI, the Chroma DB client, a Git client, and so on. Don't worry about it. It's going to be available on the web. I'm not going to run it because I already installed it. Let's just run load the OpenAI key. And this is where the fun part begins. The first thing we do is the data indexing phase, right? And the first step is data loading, to fetch all the data from the data sources. Our data source is on Git. It's this repo. And we want to store it in this local folder, which is just going to run Git. If it doesn't exist, it's going to do a Git clone. Otherwise, a Git pull, right? So let's run this cell. Running Git clone. OK. Pull completed. So we have the data here. I have very limited mouse space here. This is the content. It's mainly Markdown files and some PNGs and some Excel and some PDFs. Good. So we have it locally, but we're not finished with the data loading process because we want to use LangChain for this entire thing. So we're going to use something called a directory loader, which is a LangChain class that allows to load an entire directory of files and make LangChain document objects out of it. So I'm going to initialize this constructor here, directory loader, give it the knowledge base path in which we Git pulled into, and then run these specific loaders for using PDFs, MD, the Markdown text files, and so on. So when I run this function here, the loaded docs array is going to be populated with documents that LangChain processed out of all these files. So let's run this. Now, this function tends to yell when it encounters extension it doesn't know. This is just a warning. This is the important thing. So we have 3,712 documents. This is basically the entire GitLab repo. So now we're ready for the data splitting or chunking phase, where we split documents into smaller pieces. We don't have to implement the splitter ourselves. We're going to use the text splitter module from LangChain and use a class called recursive character text splitter, where when we define a chunk size, it aims to keep adjacent paragraphs together. If it can't do that, it tries to keep sentences together so we don't lose semantic meaning. This is very important for the semantic search. I defined a chunk size of 1,000. It's about a paragraph size, and chunk overlap of 200. That means that any two consecutive chunks will have some overlap. This is, again, required for good semantic search. So once we run the split documents and loaded docs, what we loaded here, we're going to get these split docs. Let's run it. All right, finished splitting documents. We have 56K chunks altogether. So from around 4K documents, we got 56 chunks. Now we're ready for the data embedding or vectorizing. Let's convert all these chunks into vectors using an embedding model. Before we embed the chunks, I want to do a little experiment. Let's initialize the embedding model here. I'm using OpenAI Text Embedding 3 Small. Let's see what happens if we just embed just a single string, Node.TLV 2024 rocks. Let's embed this query and console log the result. All right, so this thing here is the vector representing this string, Node.TLV 24 rocks. It's truncated, of course. It has 1,536 dimensions. That's the standard dimensionality of this specific model. Good, so that works. Now we can do the heavy lifting, which is, in this code's case, the data embedding and the data storing all in one step, in one cell. I'm going to use Chroma here, our vector database, and again, the same embedding model that I initialized. Let's focus just on this part here. I'm running a function called from documents, giving it our split chunks and the embedding model, right, defined here, and a collection name that I want to call it knowledge base 1. I'm doing it in parts. That's the loop here because it failed doing it in one step. By the way, Python didn't have that problem. Maybe it's a Node.js problem. But of course, in production, we're not going to use that. We're going to use something like async generators or iterators or stream or anything for efficient data processing. We can run it, but it's going to take 4 minutes that we don't have. Luckily, I just ran it before the demo. So let's just check if we have, let's count the number of items in this collection. Collection count. Let's run it again. OK, 55K chunks. Good. So we have all our entire knowledge base chunked and vectorized in our vector DB, and we're practically finished with the data indexing phase. Now we're ready to go to the retrieval and generate phase. What happens in real time when a user makes a query to our app. We use the embedding model, we go to the vector database, we send it to the LLM, we get the answer back, and so on and so forth. So there are some preparations to do. We start with creating a system prompt that looks like this. You're an assistant for a question answering task. Use the following pieces of context. Ooh, there's an issue there to answer the question. And this is a placeholder for the context, a placeholder for the question. This is just basically a template string or similar. Let's run this. We'll initialize the LLM, the embedding model, and so on. We're initializing Chroma again, but this time to perform read operations, not ingesting, but running semantic searches. For the first time, we're using an LLM here, so we're initializing the LLM. The model is GPT-4o. And we're running the function from existing collection, giving it, specifying the embedding model and the collection name. This function as retriever is a wrapper around the vector store that can simplify retrieving. We define top k here, so k is 6. So we'd like to get back 6 chunks of context per query, and we initialize this function here, which received our LLM that we defined here, and the prompt defined earlier, and we can use that to run queries. So let's run this. All right. Now, this is the important part. This is a simulation of our QA bot. What's going to happen is I'm going to populate this variable here with the user question as a simulation. We'll run invoke with the user question, and we'll get back retrieve chunks. How many chunks? 6 chunks, because that's what we defined. And then run the invoke and the LangChain, providing the question and the retrieve chunks as context. If you paid attention, you can see the question and context are just the same placeholders here. So the entire thing populated with context and question is going to be sent to the LLM. So, and then I'm just going to console log the response and console log the metadata. I want to see the sources. So let's try a simple question. Anyone knows what a DRI is? What is a DRI? This is something I learned about GitLab lately. Let's run it. It runs, chunking, goes back, LLM. Okay, so this is the response that we get from the LLM. A directly responsible individual, DRI, is a single person who owns decision-making authority and so on. Basically an IC, an individual contributor in GitLabese. Maybe other companies also have that term. And this is the source that it's from. It's a markdown file. Let's try another question. What is the difference between a manager, and a DRI? This is a bit more complex. It's running in the background, calling the LLM, getting the chunks, the LLM is reasoning, and the key difference between a manager and a DRI lies in the roles and responsibilities. This looks like this because it's markdown. We're not processing it as markdown, it's just text. And here are all the resources that were used to generate this. Let's try another one. This is something I was always curious about. What is the... Thank you. That's kind of you. So what is the tech stack used here? Any guesses? Any bets? Come on. 3 seconds. 4, 5, 2, 1. Okay, so the tech stack used here includes Laravel, MySQL, Terraform. Oh, so it's a PHP shop. Good to know. And maybe just the last one, more practical. I'm a developer, and I'd like to get promoted. What is the process? Sigh. As a developer looking to get promoted, you should follow these steps. Complete the promotion document, manager review, promotions review, blah, blah, blah. I'm going to pass. Okay, good. So we made it. We built an organization knowledge bot in under, 8 minutes. This is the demo code. What really happened here? We built a RAG pipeline for GitLab's company's wiki using LangChain.js, OpenAI API, and the Chroma vector database. We implemented the data indexing phase of the RAG, and then the retrieve and generate phase of the RAG, and we simulated a bot, and now we can just expose it as an app on Slack. It's very simple. But this was a naive RAG. This means that building a production-ready RAG is not as trivial. Why? This is the topic of my next talk. But I'll just say that usually what happens is that we just don't get the quality of response that we normally expect. And that usually happens almost always if we use modern LLMs because of the retrieval, not the generation, so the R in RAG. What happens? Well, the chunks that we get back based on the user's question are not optimal. They're not the best. So the LLM can't just, make up stuff where they can. We don't want that to happen. So either the prompt has chunks that are not relevant, so we get some noise in the prompt, or not all relevant chunks are returned. So either a precision or a recall problem. What can we do? A number of things like hybrid search and different context window searches and implementing there are advanced techniques that are outside the scope. You can talk to me later. It's really interesting. All right, what about building a RAG in Node.js? Well, we just proved that it's possible. We did it in real time. But truth be told, if you're considering building a production project in Node.js, you should know that not a lot of tools are available, especially compared to Python. One example is Llama Index, which is a great library in Python. This is my personal view, relevant to June 2024. Maybe the TypeScript version of Llama Index is not mature enough. I wouldn't use it right now, at least. Maybe it will change in 6 months. LangChain is more mature. That's why we use it. But even if you end up using LangChain.js or even building your own JavaScript library for LLMs, you might find yourself needing things like an evaluation framework or an observability framework for LLMs or a tracing framework for LLMs, basically ecosystem, and that's currently only partially available. So you should consider, that's up to, if you want to implement it in Node.js, that depends on the scope of the project and the use case and so on. The good news is that the LLM JavaScript community is getting stronger by the day. And if you're into that, you're welcome to contribute to it and make it even stronger. So, thank you for bearing with me today. We went over the building blocks and elements of RAG. We implemented, I implemented, but you guys helped a lot, so thank you. A RAG live in JavaScript on Node.js, and we just touched a little bit on what needs to improve for production. I hope this has been helpful and informative to you and as enjoyable to you as it was for me, so thank you very much. I'm going to be around if you have any questions. You can reach out to me via email, LinkedIn, and Twitter. And if you're into security, check out Blink, the world's first security automation AI copilot. Thank you very much.